landscapes. Well, it turns out the topology is the same. It doesn't matter which landscape we're looking at, and that's the main result, pretty much. And it's a joint work with Mark Goreski who is at the Institute of Advanced Study. So in the best traditions of mathematics, let me just state the problem straight away. So the setup is as follows. I have a matrix, n by n Hermitian matrix. This is my Hamiltonian with spectrum labeled in the increasing order. And I also have a subspace of dimension little s. And I will define the compression of my matrix B onto the subspace S by starting with S. Then it is included in Cn, then I'm acting by B, and then I'm projecting back to S. This is an inclusion, which by now is a bit a dangerous word in the US, but yeah, I'd like to point out that this is yes, I'll use some projections instead. So. And now I'd like to choose and fix K. Number between 1 and S. And consider the eigenvalue of this guy. And I'll call it capital lambda K. And I want to consider it as a function of S. So now this lambda K is a function from all possible subspaces. All possible subspaces live in the Grassmannian of S-dimensional subspaces of Cn. And the eigenvalue I get is a real value. And the question is, look at the graph of this lambda K. What can we say about its topology? So the general question is the topology of the graph of this function lambda K on the Grassmannian. And by topology, I mean I want to understand its critical points. In particular, its minima. Can it have local minima that are not global minima? Local versus global minima. And so on. Just to give you an idea of how it may look like, let me show you some pictures for a simple example. It's a little bit of a cheating example because it's difficult to work with complex spaces, too many dimensions. So I'll restrict myself to real space. And the example is, while it's warming up, let me point out what's the setting of the example. My matrix B will be diagonal. Here we can just change the basis, right? So it doesn't pay to have a different matrix. Diagonal matrix with distinct eigenvalues. My Grassmannian, this space, I'll plot lambda k on the two-dimensional subspaces of R3. So S is equal to 2, so I have two eigenvalues to choose from. And hopefully by now it warmed up. And this is the function. Well, these are both eigenvalues here. The lower eigenvalue and the upper eigenvalue. Somehow I introduce Cartesian coordinates on my Grassmannian. It's not, it's kind of, it's a projective space. Huh? It's a projective plane. It's a projective plane, but somehow I introduce Cartesian coordinates, and we see some interesting features. So the minimum of the lower one is a whole line of points. The line there behind us, it's the same line. It's actually a circle because by the time we get to here, we're already there. So it's a little bit difficult to understand the full topology on this in these coordinates. The maximum is here, also a line, but it ends. Kind of, it's not a full line. It has endpoints where the top eigenvalue, where it starts colliding with the top eigenvalue. Now this line continues as the minimum of lambda 2 now, and the maximum of lambda 2 is another line which is actually a circle. When I asked Gemini to produce me a plot, it made much better plot than this. So AI was better than, this is AI assisted talk. Here is Gemini's version of this thing. So it basically said you're an idiot, like the planes are parameterized by the normal. So we can plot the same function in spherical coordinates. So depending on the normal defines the plane. And in this direction of the normal, I'll plot the eigenvalues for you. And now it becomes a surface. Beautiful surface. Also not completely perfect because normal, we need to projectivize in our head. But now we see the minimum. This is lambda 1. The minimum is a nice circle, and the maximum is this arc of a circle. The color scale by magnitude of the eigenvalue. So this is the minimum, the smallest. So in the direction of the normal, I'm plotting the point which is the magnitude of the eigenvalue. That's the way it's plotted. Make sense? So this is the smallest distance from the center somewhere in between is the smallest eigenvalue, and this is large. No. It's just for enhancing the visual, yes, visual perception. Also, the lighting is there for beauty. Level. Yes. Yes. Yeah, but the question is whether it just corresponds to distance from the origin as well. It could have been a gray, but we can see that this is the maximum and this is the minimum. Yeah. All right. Now, of course, this bubble fits inside that bubble. This is second eigenvalue, and then this special points where it's not smooth coincide with these points. I shouldn't be touching the screen, sorry. These points, which are also not smooth, which are the endpoints of the kind of the minimum curve. So these are the things I would like to understand, and I'd like to understand them from the point of view of Morse theory. Mm-hmm. Yeah, so it would be nice and smooth. So it would now be in three-dimensional space, right? In two-dimensional. It's still a projective plane. Yeah, it would be a nice and smooth function because it doesn't have anything to collide with. I would think it would be just some I don't know, ellipsoid shaped. Mm-hmm. No. Zay was asking s equal to 1. So one-dimensional. Yeah. So if we take s equal to 1, then it's just the quadratic form. We're plotting the quadratic form over the sphere. Yes. It's not super interesting. Sorry, Susanna. So these guys S's are planes in R3. In this picture with the normal, yes.
Okay. And the matrix has distinct eigenvalues. So why the minimum is a circle?
The minimum is a. It's an excellent question. Let me point out some more features that are shown on this graph that I didn't mention. There are these red points, and they will come up in the talk. So the red points are special. We call them special points. They're the special S's that are composed of the eigenvectors. So one of these two red points is the linear combination of the first eigenvector and second eigenvector. Another one, first eigenvector and the third eigenvector. On both of them, lambda 1 would be the lowest eigenvalue. It gets the lowest eigenvalue. In fact, this whole circle is the circle of S's of planes that contain the first eigenvector. Yeah, this is very relevant. Similarly, like this waist is a circle that contains the top eigenvector, and this combined circle is the middle eigenvector. Yeah. All right. So I guess I can keep this picture on. So let me summarize some of the things we saw in this picture. So mins and maxes and other critical points probably in higher dimensional setting are not isolated. They lie on submanifolds. Never mind. They're not isolated. They're some sort of submanifoldish structures. Lambda k is not smooth. Has this annoying points where it loses smoothness. But it's continuous. Bounded. Just by Cauchy interlacing, each lambda k lies between bk and bk plus n minus s, where this part is the perturbation, is the rank of the perturbation that I did by restricting my matrix to a smaller subspace. Has directional derivatives. So not smooth. At each point in every direction, we can compute directional derivatives. I would like to explain this topology in general dimension, using Morse theory, and this creates some problems, the lack of smoothness, that the critical points are not isolated, but we'll go through this step by step. For now, I'd like to just summarize informally the results. The backboard is not very usable. So first of all, we find that lambda k is a perfect Morse function. In the appropriate sets, on the Grassmannian, on the space that it's defined on. The perfect Morse function means that it has as few critical points as possible. In particular, it doesn't like to have local minima that are not global minima, because that would be too much. It doesn't have any extra critical points. The critical values, the values where it's critical, probably doesn't come as a surprise now that we've seen the picture, are exactly the eigenvalues of the original matrix. Those that lie in this range where the function lives. We can compute the Morse index, the number of directions in which it's decreasing at every critical value. The Morse index at a critical point. So we saw that the critical points depend on the level in which they belong. So at a critical point S such that lambda k of S is one of these critical values, so it's some Bm. The Morse index is 2m minus b, minus k. So this is twice the spectral shift. Spectral shift. So basically, this guy was an eigenvalue of B. So spectral shift between B. And now it's eigenvalue of this chopped up restricted BS. And we just subtract the indices of this guy in the two spectra, multiply by 2. 2 is a little bit weird maybe, but keep in mind we're in complex space and the real function, so kind of over reals, it's natural to have some factor of 2. And something that we talked, Susanna asked about, is that the critical set is a submanifold with boundary. The critical set is a submanifold with boundary of the sub-Grassmannian. So it's the Grassmannian S and it depends on the eigenvector psi. It's all my planes S containing the given eigenvector, psi m eigenvector. Yeah.
There was an interesting boundary from the point of view of the most boundary of this subdomain.
Yeah, excellent question, and the answer is after a bit of hard work, no. So the boundary is not. Yeah, it collides with another eigenvalue. It is non-smooth there, but from the point of view of Morse theory, there is nothing going on there, and that's where the work is.
You have some degeneracy. So you mean the pure Morse mixes?
Yeah. So okay, I'm stretching the truth here because I said it's informal. So when I can compute the Hessian, we compute the Hessian. When it's smooth, we compute the Hessian, and this is an honest Morse index. In answer to the previous question, kind of nothing. There is also a notion of topological critical point that I'll go over, and it's not happening at these boundaries either. So we have a. You will see in the proof there is a perturbation that allows us to like get rid of this guys. But to comment further on your question, and oh yes, sorry.
So, because your information matrices, they have a basis of real eigenvectors.
Mm-hmm.
If you want, if you ask the same question replacing C with R, do you get the same thing but with the Morse index replaced with n minus k, or is the different? Is the theory different?
Yes, you're right. So yeah, if we haven't worked it out carefully yet, I'm sure that what you're asking about this too, it will disappear.
Yeah, and then that should be the only real change, right?
In here there is a hidden like what do you use a ring for which coefficients for your homology you're using, and then because Grassmannians in Z the homology is particularly nice. It like skips every generation, and in R there is torsion. So there are some difficulties.
Okay.
Difficulties there, yes. But yeah, on the other hand, before I was only thinking about real case. I was scared of it's kind of first serious foray to honestly consider complex. So yeah, there is some benefits, there are some losses. Yeah, what I wanted to say that about this these boundary points here, kind of it is still like all points along here are minima, and at this point it's also a minima. It's just flat from one side and then falls off on the others, and you can yeah. Okay, before I define actually terms and conditions that I'm using here, you're probably wondering why the hell even considering this thing. So let me give you some motivation. So my original motivation, personal, was the nodal universality conjecture. Originally proposed by Uzi Smilansky with various collaborators. Vaguely formulated, it's if you count the number of nodal domains of some sort of model like Laplacian on a regularly shaped domain or graph, then this number of nodal domains will have a Gaussian distribution once you rescale it appropriately. In particular, it's very nice, can be carefully formulated on quantum graphs, and it has not been falsified. There are no examples where it doesn't hold. There are some examples where it does hold. So how is it connected to this? There is a nodal magnetic connection, connecting nodal statistics of the nodal domains, roughly speaking, to Morse index statistics on so-called magnetic torus. So in a graph, you introduce all possible magnetic fields. And this is due to myself, Yves Calan de Verdier, and Tracy Bain in several papers. Now, my collaborator Aimé Bantz proposed to use Morse theory, and this is kind of going towards using Morse theory to understand Morse index statistics. So this magnetic torus here can be realized as a submanifold of my Grassmannian. It's a Grassmannian on, suppose you have a graph with n vertices, then it's a submanifold of the Grassmannian. You up the dimension by the number of cycles in the graph. So this question I'm posing is kind of a toy problem, really. I want to understand if it's possible at all to talk about Morse theory. What can be said about Morse theory when this eigenfunction is non-smooth? But there are some links. So another motivation in spectral minimal partitions, question introduced by Susanna. There is a conjecture that once you find the local minimal of your partition, it is the global minimum in a class of partition of the same topology. This would be a great tool because you find a minimizer, you can compute the Hessian, you can establish local minimality. It would be great to conclude it's globally minimal. And these results say that if your space of perturbations is very large, then yes, you can do this. Unfortunately, in all practical cases, there is some smaller space of perturbations you need to consider. In quantum chemistry, this sort of pictures, this sort of questions arise as in Born-Oppenheimer approximation, very common. And last but not least, we had many talks in the numerical analysis of eigen spectrum. So this my BS that I defined is really, we've seen it in several talks. It's the projection method. So it's surrounding B with projection operators onto S, and then chopping it up, kind of removing all the zero parts. So this is projection method. And the name Ritz values, Ritz landscape comes from there. And we see in this results in this one, the critical values are the eigenvalues. These are the true eigenvalues. Are the true eigenvalues of B, which implies that if you have spectral pollution, you get some eigenvalues that are not coming from B. It's not critical point, so it's unstable if we start varying the projector, on the space on which we're projecting, is unstable with respect to varying the projector P of S. Can it be used? It can be used.
So if you have so projection method, say, is describing functions in a particular basis. So I could take, I could change the method by changing basis. And then suddenly my spectral pollution may not be present in different bases. So with this phrase,
Can it be used infinitesimally? You kind of change your polynomials, I don't know, space a little bit. So it's this is unstable infinitesimally, even. You can see them move, maybe. Has it been used?
so you need a basis.
Uh-huh.
Generate that basis by taking values of Jacobi.
Mm-hmm.
You vary the weight.
Yeah. Yeah.
I don't know if this has been done.
Yeah. Can it be useful? So that's the question. All right, good. So let me now spend, I think I'll keep the results so we can refer back to them. Let me know if you want me to expand on any of the motivations that I just removed. I want to define, so the first result was the claim that it's a perfect Morse function. Let me try to explain what it is. This is probably the most interesting kind of new to me at least term that we worked with. So the perfection I'm talking about is homological perfection. And there is also the classically perfect Morse function. So if a function is Morse, if f is a C2 function on some smooth manifold M into R, and with non-degenerate, in particular isolated critical points, then the definition of a perfect function is that the number of its critical points is equal to the sum of the Betti numbers of the manifold. This is a very crude version of Morse inequalities. You can go deeper by classifying critical points by their index, and they give individual betas. But this is that. So we have a minimum, and Morse theorem says that this is the minimal possible number of critical points. Okay, we are not C2. We are not the critical points are degenerate. So what can we deal with? Let's first look at this and look at some examples. Nice function on a torus, as is traditional. I'll consider the height as my function. So this is the minimum, and this is the maximum, and there are also two saddle points here, versus topologically the same torus, but the height function is different because now I have two saddle points and still one. Sorry, two minima and still one maximum. So this is perfect. This is not perfect Morse function. And if my torus is a bagel and I just let it lie flat on the table, then its minimum is a whole circle, and its maximum is another whole circle. It's a perfectly shaped bagel. So this definition is not applicable. Let me now try to extend it by looking a little bit more detailed on the homology of sublevel sets. So for the first example, what I'm looking at now, I imagine cutting the torus off at different levels, and as levels progress, we'll get different shapes. So before we cut anything, this is boring. So the first part where sublevel set is anything interesting is when we cut off the minimum. And here we have, homologically, we have one zero cycle. Like it's a one connected component, basically. There are no loops in this space that are not contractible. As I'm moving up, sooner or later, I'll hit this saddle point. And very soon after, I have something like this. It's still 1 0 cycle. But now, after I hit the saddle point, I can put a little loop around here, and it cannot be contracted, and I'm not allowed to slide it off the boundary. So now I have one cycle. And I continue building it up until I hit, it all remains the same topologically, until I hit the next critical point, which is the saddle here. And now I have a cycle still like this, but also I can now squeeze another cycle going like this, and it's not contractible, and it's not the same as the other one. So we have another one cycle, and then finally, once everything together, the two cycles are a little bit hard. Well, I do not know how to imagine them, but there will be 1 2 cycle after we're done chopping it up. This is the process of sublevel set evolution for this one, which we said is perfect by this criterion. So how about this one? Let's say the minima is a little bit mismatched. So at some point you have 1, and at the next point you have 1, and then also another. But we haven't reached the first saddle point here yet. So at this point, I have 2 0 cycles. What happens when I move past the saddle point? I get a shape like this. It's now connected, so it has 1 0 cycle, and there are still no 1 cycles, which is interesting. When I move past the next one, it kind of goes as before. Now I have a cycle running this. I can slide it around, that's okay. I cannot slide it off, I cannot contract it. So it's 1 0 cycle, and now 1 cycle, and the rest continues as before. So what's the difference between these pictures? Or these processes? The difference is that here we were only adding cycles, and here at some point we added too much, and at the next point we destroyed it and then added other stuff. Well, this is basically the definition of homological perfection. So the rigorous definition is we have F, which is sufficiently nice. It's H, homologically perfect, if for any values A smaller than B, and for any R, there is an inclusion in the sublevel sets. The part of the manifold that lies below A is included in part of the manifold that is below B. And this inclusion induces homomorphism on the homology of any rank. So cycles that are in here are also cycles in there, basically. However, some cycles may disappear, may be identified. There is a quotient going on in the homology, may be identified. So if this is injective for any such things, then it's H perfect. So this is injective. This is the condition. But it is equivalent to think about this less formal picture, say that the cycles are only created. Cycles are only created, never destroyed. And if you heard about persistence homology, then persistence barcodes, they track the creation and disappearance of cycles. So in a persistence barcode, all bars are infinite. They're semi-infinite. They start somewhere and never get chopped off. So this is a nice convenient visual. So this is what I mean by perfect Morse here. For critical values, what is the time constraint? Yeah. No, I mean 10 minutes before 12 or 5 minutes or 12. You're too kind. Oh, there's a clock. Perfect. Ah, no. Okay. Ah. Oh, no. I have a thing here. I thought this is counting down. So how do we define critical values? One way to define critical, there are critical points and critical values. The critical values are those values that we can understand them as values taken at a critical point. But for the definition, it's better to define it as not regular values. And we have a couple of tools at our disposal. We can do differentially regular. It's a nice function. It's Lipschitz. So we can use Clark's subdifferential here. Or we can use topologically regular. And this asks if passing through a value, the sublevel sets changes dramatically, and changes dramatically in a topological sense, or doesn't change dramatically, means it's a deformation retract. From one level to another. And homologically regular a point is homologically regular, a value is homologically regular if the homology of M below the value, so value C. We're talking about a value C if, above value relative to below value, homology is 0. Basically means that the homology does not change when you cross this value. That's what we were doing here. We were working with this definition, essentially. And then nicely ordered by inclusion. But for eigenvalues, we can take one-sided derivatives. So actually, we can do differential definition and then get the rest. All right, that's basically all the terms and conditions. As I mentioned, the Morse index we honestly compute only at the points where it's smooth differentiable. But you kind of saw that along the whole critical set, it feels the same.
Is it the case that if you are, say, H perfect by sort of minimality, they all have to be equal, or
Say it again. If you are H perfect, then what?
then by the minimality
Uh-huh.
they will all have to be
Who is the? Oh, this things. No, I think you can come up with something that is H perfect and there is nasty differential sense. So yeah, I think this is a reasonably nice case. Yes, we are not smooth, but we have one-sided derivatives. Okay, so let me very quickly, I give myself 5 minutes to do so, hint at the proofs, how the proofs go. So this is by far the most difficult part. Critical values, this is done by perturbation theory. Just take derivatives. Use, what is it, first variation, the Hellman-Feynman formula. The Morse index, there is some Schur complement gymnastics going on there. No, but by now I know the routine. I have several papers where similar results are proved, so I just do this, what's it called? Do the gymnastics, the standard program or but for perfect Morse function, this is the basic idea. Let me warm up the machine again. So it is a fact that if we look at the trace, so let's define function Ts as the trace of this guy. Now, this function on the Grassmannian is actually smooth. Morse in the classical sense. So isolated critical points and perfect. This is known. It goes back to Bott. Basically, he used something like this in the proof of Bott periodicity, but then it has been rediscovered again and again. Probably he was also not the first one to observe it. And let me show you. Let me define what we do with it. So it's smooth Morse perfect. Its critical points are the special points. So these are the points where we take a span of some collection of eigenvectors. So we understand it really, really well. So let's then perturb our lambda by this trace. Okay, it doesn't resolve the singularities, right? If it was non-smooth and we had a smooth function, it is not going to become smooth. So all the eigenvalue multiplicities, they stay there. It's not a solution to that. But something else happens, which is nice. We can also write this maybe a little bit artificially as kth eigenvalue of my matrix plus this function Ts multiplying identity matrix. Why I want it to be an eigenvalue of some matrix family. And now the TV has gone offline. Yes, thank you. Good. So So this guy is a picture of the trace alongside the others. Okay, it's nice and smooth, has a maximum, minimum saddle point. These are the special points that we saw at the same locations in the others. But what's more important is what happens to this function lambda epsilon, as this is the plot of lambda epsilon. And where we previously had whole submanifolds of critical points, now we have isolated critical points. This is a saddle. There is a minimum somewhere far away there. This is a maximum. So suddenly the critical points that are smooth are isolated. And the points where we had non-smoothness, they're not critical anymore. And that's what I meant when I was answering the question. This do not contribute to homology. Just think in your head, what would happen if we were to smoothen this thing here? It would be not a critical point. There is a direction in which before and after this point I'm increasing, so it's not a critical point. And same on the upper sheet. And we have a theorem with my colleague Igor Zelenko that allows us to prove that this is the case by some differentiation. I think this is a good place to stop.
Question about the trivial case, one-dimensional case.
Mm-hmm.
You said there is nothing to collide. So from which I infer that there is something there when these two, in your pictures, where the two eigenvectors collide. Is there something that, some sort of collision going on that explains singularities?
Yeah, well, by colliding, I meant these points where two eigenvalues are coincide. No. We know from perturbation theory that if as long as eigenvalue is simple, it is smooth. So only at these points we have singularities. Yes. So this is even. And for the like when we look at the so the trace and one-dimensional situation is kind of the same. So the picture for s equal to 1 would be this guy.
The theory goes through if you look at, say, an operator with compact resolvent, you take S to be some finite number, K below that. I mean, of course, then you don't have the sort of, it only makes sense to look at minimum, I guess, rather than maximum, but.
This is a natural sort of next question to consider. So allow yourself S-dimensional subspaces of the whole Hilbert space with a nice operator and see how much of this carries through. This would be the next step. I expect everything, well, with reasonable adjustments, as you mentioned, no maximum, for example, if it's bounded from below. It should go through, but of course it's a more difficult thing and infinite dimensional Grassmannian and all this stuff.
Do you expect that there's actual really different things in the analysis, or that it's in fact the same analysis would make it correct?
I have not. It's like the next logical step, and I have not thought about it. So feel free to think. Yeah, take it up.
I think the analogies to approximation theory would be quite relevant when you're thinking about the eigenvalues, the minima of these objects for infinite dimensional operators. So in particular, I don't know if this is true. So you could consider a collection of orthogonal polynomials that arise as eigenfunctions of a strong real problem for the weight.
Mm-hmm.
Keep everything else the same, and I change the weight. This is my perturbation.
Mm.
Now we'll get a different family of polynomials.
Yeah,
I think this is the correct way to do this analogy? And then perhaps, I don't know, perhaps what will change is that instead of getting lambda k of the projected operator of the subspaces plus epsilon t, maybe you will get a function of epsilon times a function of t, but maybe not the exact same thing. So this smells like backward error analysis to me.
Okay. Yeah. Yeah. I'm not. So T here is a particular perturbation we used in the proof, but you can. So of course inside all the computations we are, there are projectors here. Like forget about this guy, and then we start varying the projectors and trying to understand what is the what's
So numerical analysis, the backward error, the spirit of the backward error analysis is what you compute is not the exact object you're computing, but it is in fact the exact object corresponding to a slightly perturbed problem, right? Which is exactly what you right? So you're not computing lambda k b restricted to S, you're computing lambda k
of a perturbed B. Yeah, that's an interesting perspective. Yeah, I have to think about it.
Yeah, I don't think it's very
Try the actual clinical values of lambda k. So is that kind of the minimum, there is this minimality property, but are they, it's easier. Okay.
Yeah. So we understand.
When you do this perturbation, you are somehow selecting some of the critical point of T of S.
Oh.
My question is, can you actually have a path going from lambda k to the trace that keeps the property all along this deformation, or it is just something to
I think probably if you would just interpolate, so put 1 minus epsilon here. Yeah. Yeah, because for any epsilon, it has the same critical values, same critical points. So once epsilon is non-zero, this whole submanifold, it's selecting points. Yeah, and they will stay the same. So like we have this critical submanifold, so the minimum on the circle here. But there are these red points. Once I start perturbing, one of them will become the minimum, isolated minimum, and one will become a saddle point, and it will stay for all epsilon until I reach, until I blow up to this point. So this one will be, I guess, minimum, and this will become this saddle point, but the location stays the same, and the values are easy to compute from here. So it's really, if we just look at the isolated eigenvalues, and this is what we're interested in spectral optimization of an isolated, like minimized third eigenvalue. But yeah, if you start perturbing it, it becomes a little bit more manageable, it seems. It's one of the lessons.
critical points are created along the deformation.
Okay, I say, yeah, we just honestly differentiate and show that at all other points other than the special point, we can always find a direction in which everything is growing. There is a slope.
You say things are kept for across epsilon, but there's presumably some large enough value of epsilon where you will have some new critical points being created.
I don't think so. I have to check the proof. I feel that I may be lying, and we do the proof for small epsilon because this is the limit we want. We want to come back to 0 epsilon. But I'm fairly certain that this situation persists for all epsilon.
Assuming no. No, okay, but so I'm trying to think of how it's
Um,
So in the original problem, so
Yep.
B,
mhm.
it has eigenvalues which could cause.
No.
I'm not. Yeah, I'm not assuming they're not. Yeah.
Yeah, so what you do there, because there you take a subspace. So you
Yeah.
have a dimensional subspace. And so if you put, so you've got this degeneracy.
Can I just interject very quickly? So this homologically perfect is sometimes counterintuitive. A constant function is homologically perfect because all the homology just gets created at this point, never destroyed. So things can degenerate quite significantly without breaking the theorem, but just the theorem is a little bit less informative in this case. Yeah. The same, yeah. Then it's a constant, but it still holds. Still holds, yeah.
Trying to think through the perturbative, like what's happening.
If you,
Um,
yeah.
Lunchtime.